All right, welcome back. So this is the continuation of the introductory lecture, video 2 of the introductory lecture, where I'll start with discussing those examples in more detail, right? So last time we finished off by discussing this fact, right, that extremal metrics in conformal class correspond to harmonic maps, extremal metrics in the space of all metrics correspond to minimal immersions. And we know, as I mentioned, so that those are maximal metrics for these corresponding surfaces, so there has to be the corresponding minimal immersion, right? So let's look at the corresponding immersion. So to do that, for S2, for example, we need to know the eigenfunctions, right? So this is another example where you can actually compute everything by hand, but that still takes some time. So I'm not going to do that. I'm just going to give you the answer and just some idea of how to do that. So the eigenfunctions of S2 are restrictions of homogeneous harmonic polynomials on R3. So you take the ambient R3, there you have some polynomials, which are harmonic and homogeneous. You restrict them on the sphere, they're no longer harmonic on the sphere, and it turns out they're actually eigenfunctions on the sphere. All right, so let me give you some examples, and then I'll just say one word of how one can prove this. Right, so the eigenvalue is this. The eigenvalue is just a function of a degree. And for example, in degree 1, we just have x, y, z, so any degree 1 polynomial is harmonic. It's no longer true for degree 2. For degree 2, the corresponding eigenspace is spanned by those 5 functions. All right, so the way to prove that is basically you can do the following. You can take those polynomials, you can write Laplacian in the spherical coordinates, and check that indeed when you pass to those spherical coordinates and you compute Laplacian spherical coordinates, you can see that the fact that it's harmonic in R3 implies that these polynomials are, in fact, eigenfunctions on S2, right? So this tells you the eigenfunctions, and once again, you can actually show that those form a complete basis. Those restrictions form a complete basis, which tells you there's nothing else, right? So there's one way to do it, similar to what's done for the torus, right? So now what does it tell? So we know that round metric is a maximal metric for the first eigenvalue. So what does it mean? It means that there exists a map from sphere to sphere, to some sphere, right, to Sn. Let me go back here to this theorem. Right, so we know that there exists a map to Sn for some n, right? We don't know exactly what n is, by the eigenfunctions, lambda 1 eigenfunctions. Right, so let's look at this one more time. So we have the first eigenspace is formed by x, y, z, and you want a map to Sn formed by some functions in this space, right? And it's basically it's obvious, right? So the more I talk about it, the more obvious it becomes. The identity map is the map that you're looking for, right? So the map from S2 to S2 is a minimal immersion, and it's a map by eigenfunctions whose sum of squares is identically 1. Right, so this is very straightforward. Identical map is what you want. So for what happens for RP2? The best way to look at RP2 is usually via the antipodal projection, right? So the object in RP2, any object in RP2, is an object on S2, which is invariant under this antipodal map, right? So in particular, eigenfunctions on RP2 are eigenfunctions of S2, which survive this projection, right? So which are invariant under antipodal map. So antipodal map stands x to minus x, y to minus y, z to minus z. So the polynomials that survive are exactly polynomials of even degree. Right? So the first eigenspace in RP2 is spanned by those functions. And the goal is to find, for us, right, to tell us that there exists some collection of functions in that space whose sum of squares is 1. Right? So I should tell that those are not these functions, but you can play with linear combinations and get that, for example, this is a perfectly legitimate map. Right? So this is all these functions are in this space, and you can check that sum of squares is 1, and you can also check that it's an immersion. It's isometric immersion, right? So the induced metric tensor is the round metric. So what about the torus? So I didn't write anything about the torus, but it's kind of straightforward that there exists something like that, right? Because as we've seen, the eigenfunctions are just exponentials, right? And the norm of exponential, the complex exponentials, just sines and cosines. And sum of sine squared plus cosine squared is exactly 1, right? So it's obvious that there exists a map. And in particular for this equilateral torus, there would be map from this tau2 T2 equilateral to S5. Right, it turns out that this equilateral lattice is the only lattice which has multiplicity 6 as a first eigenvalue. Right, so the dual lattice again will be equilateral lattice, but with different angle. It'll have 3 vectors corresponding to it will have 6 vectors of lowest length, and those vectors correspond to the 6-dimensional eigenspace. I'll leave it as an exercise. I'm not going to write the formulas, but it's kind of obvious because it's sines and cosines, and there has to be some squares equals 1 in there. All right, so those are some basic examples. So what can be what else can we show? What are some other examples? You can actually show the following. What happens for a Klein bottle? And it turns out that the answer is it's impossible to obtain this answer without knowing the connection with minimal surfaces, right? So for example, the result for the sphere by Hirsch was obtained without any connection to minimal surfaces, right? He just proves the inequality. It turns out that for the sphere, it's equality. Li Yao is the same thing, right? So they prove inequality, but it turns out it's equality for their own metric. But starting from a result on the Jarashvili for the torus, the strategy is a bit different. Right. So now what we're doing is that we're first showing that there exists a maximal metric, which is smooth. And then we try to use connection with minimal surfaces to identify what this metric is. All right. So this follows the same pattern. I'll talk about existence theory right after this. But for now, let's assume that the maximal metric exists. Right. So what's proven in those 2 papers is that there exists only one, right? So they exist with this tau tilde 3, 1. It's a minimal immersion from Klein bottle to S4. And what they prove is that it's the unique minimal immersion of Klein bottle into any sphere by first eigenfunctions, right? So for any other minimal immersion of Klein bottle to any sphere, the coordinate functions will not be first eigenfunctions. And this tells you that this metric is the only metric which is extremal, the only critical point of this functional. And if you combine it with the existence of maximizer, you get that this has to be a maximizer. Right? And the exact value of this is not that important, right? It's some transcendental number which you can compute, but it doesn't clarify much. That's good. And there's only one more example which is known, where the explicit value is known. And this is the first eigenvalue on a genus 2 surface. Let me quickly describe, because this is where this word branched comes into play. So what you need to do, you need to take S2 and view it as a Riemann sphere, right? Just C with infinity. And you take a hyperelliptic cover of this with branch points at this point that I drew here, right? So it's the section of unit circle with axis 0 at infinity. Right? You take hyperelliptic cover of those branch points, you get a genus 2 surface with this equation, right? So you look at this equation, this surface in CP1 cross CP1 technically, and you consider the metric on the surface, which is a pullback of the metric from the sphere. Right? If you think about it, it already should kind of worry you a little bit, because the pullback of the metric is only defined for diffeomorphisms, or at least for local diffeomorphisms. If you have a branch point, then the pullback metric will not be an honest metric. It will be what's called metric with conical singularities. And I'll talk about them in a second. But what is why is it not a real metric? It is a real metric, but why is it not just a smooth metric? So what happens is that if you so imagine that this is a picture on the genus 2 surface instead of the just picture of the sphere, right? So what happens if we go around this branch point once? So what happens is that as we go around once, right? So on one hand, we do a 2 pi angle, but we actually don't come back at the same point. We come back at the same point on the sphere, but on the surface, on the hyperelliptic cover, it will be points on different leaves of the cover, right? So when you go around the branch point, you come back at the opposite point, the same point on a different leaf, and you need to do another loop to come back at the same point, right? So those points will have angle 4 pi around them instead of usual angle 2 pi. Right, and those are called metrics with conical singularities. It turns out that those are singularities analytically, right? So everything I was talking about before, it's very, it's analytical. So from analysis viewpoint, those metrics do not pose any problems, right? So you can just, if you define the eigenvalues of Laplacian using the same formula, using the variation characterization like I did before, then this is everything is exactly the same. Right, and this is how people work with such metrics in the context of this maximization problem, right? It turns out that this is a natural class to consider for our problem, right? So it doesn't necessarily exist smooth maximal metric. Sometimes the maximal metrics could have those singularities. And the one thing, so I'll actually, in the next video, we'll actually clarify why they appear. Right? There'll be very explicit calculation that show why they should be there. Right? But for now, let's just leave it as this. I don't want to go into too much detail about them, right? But the point is that it's just some points where the angle around them is not 2 pi but more, right? So it's like in the cone. If you look at the cone is perfectly normal Riemannian manifold outside of this point, where if you go around, the angle will be not 2 pi but something else, right? So those points are exactly the same. Only for cones, the angle is usually less than 2 pi. Here, the angle is bigger than 2 pi. All right, so let me cover the existence of maximal metric that I promised. So for simplicity, I'm just going to state the results for the surface of genus gamma, orientable surface of genus gamma. You can state the results for non-orientable, but they are a bit more cumbersome. So it's a result by Roman Petridis, who is another speaker on this on the seminar. He's actually speaking about something related. I'll comment at the end how his talks relate to what I'm talking about. So he showed the following. Assume that you have this Montanistic condition, that the first eigenvalue of genus gamma is strictly bigger than the first eigenvalue, maximal possible first eigenvalue on genus gamma minus 1. So he's saying that suppose this is true, then there exists a metric which is smooth outside a finite number of conical singularities. Right, so let me comment about this condition a little bit. So why is this condition first natural and second necessary? So what you can do always, so let me take genus gamma, suppose gamma equals 2, right? Just so I can draw a picture. And I'm looking at genus 2 surfaces. I want to show that there exists a maximizer, right? So what I can always do the following. I can take my equilateral torus, right? So this is the maximal metric on the torus. I cannot really draw it, but suppose this is it. Right, so what I can do, I can take a tiny handle. Excuse me. I can take a tiny handle and attach it to it. Right, turns out this is not, it's some work, but not necessarily too much work, to show that you can do it in a way, right, that area converges, right? This is just tiny, tiny handle. And the spectrum converges as well, right? So it's a tiny handle whose length going to 0 and whose circumference is going to 0, right? So it's just collapsing handle. The resulting metrics are metrics on the genus 2 surface, which converge to a value on the torus. Right? And so those are possibly maximizing sequence for the functional. Right? Those, and there's no way to kind of rule them out, right? So they always could be there. So degenerating sequence where one of the handles is collapsing. And so what they're just saying is that if it doesn't happen, then if we know somehow a priori this is not the maximizing sequence, then nothing else could happen, right? So the only bad situation is this situation, right? So this is one way to describe the theorem of Roman. And then very recently, it was proven that indeed this inequality holds, right? So for any, and this is not very, not easy at all, right? So it's just very long and technical paper where shown that this inequality is true, right? In particular, maximizing metric for lambda 1 always exists, right? So the talks by Roman are going to be about very similar question. He's considering Steklov problem, which has very similar connections to minimal surfaces, only for free boundary minimal surfaces. And there's a similar condition that's appearing in that area. And if you're curious about, and you also need to prove similar conditions to show the existence of the maximizer. So if you're curious about how this works, I recommend you watching his talks where he'll clarify at least a little bit of how the corresponding factor Steklov eigenvalues works. And then this should shed some light on how to prove this. All right, so the upside is that there always are maximal metric for the first eigenvalue. Right, so, but this actually leaves some questions. For example, it tells you it exists some maximal metric, but it's possible there are some metrics which are maximal, but not smooth. Right? There's somewhere here, there's a smooth maximal metric, but somewhere over here, there's very degenerate and very nasty maximal metric. Right? So let me talk just 2 words about regularity of maximal metrics. And for that, you need to first define what are the eigenvalues of a not regular metric. Right? And here you can actually do it with very non-regular metrics, right? In particular, you can define something which is called eigenvalue of a measure, right? So you fix M, you fix a conformal class, and you take some radon measure on Mg, right? So radon here, I'm just saying words radon to say that the continuous functions are integrable with respect to this measure, right? And all you're doing, you're looking at that definition that I put at the beginning, right, with the variation quantization of lambda k, and you're replacing the integral at the bottom. So previously it was dvg. I replace it by d nu, integral of the new measure. All right, so the key point here is that, so here on top, you have g, but on the left here, you have only from a class of g. Right, so the key feature of this is that in dimension 2, this integral is independent of the conformal class of, it depends only on the conformal class of metric g, right? So if you take a different metric g in the conformal class, you'll get the same numbers, right? You get the same integral in here. And again, this will be a little bit elaborated in the next video. Right, but once you define those, you define some numbers. Those numbers might behave very wildly, right? So you don't necessarily form the same sequence going to infinity. But if you ask for this map, so sorry, I use different notation here and before. So it's the same as H1, right? So if I use the same, which is different notation for H1, right? So previously I discussed that this properties of spectrum, they just follow from the fact that H1 to L2, usual L2MG, is compact, then all the properties of spectrum follow. So here I'll ask this. I'll call the measure admissible if this is compact, right? So it's not always true, but it's true in a variety of cases. For example, if mu is concentrated at a point, then it's not admissible. But if mu is concentrated in a curve, then it is admissible. And actually, if it is concentrated on a curve, this number is something which is very related to Steklov eigenvalues, a topic by Roman Petridis. Right, so once you ask for it, you have those eigenvalues. But note that those eigenvalues a priori have nothing to do with eigenvalues of metric. The only thing you know is if mu is the measure, is the volume measure of the metric, then you get back the eigenvalues. But a priori it's something wild. Well, what you can prove is that actually if you consider corresponding normalized eigenvalues like this, it turns out that they are always bounded by the same number as for measures, right? Which is non-trivial fact. And moreover, the equality is if and only if this mu is a volume measure of some maximal metric in the conformal class. Right, so this is what I call regularity of maximal metrics, right? So not only maximal metrics, but regularity of maximal measures even, right? So even if your measure is wild, you still cannot exceed the value, and if you achieve the value, then you have to be usual measure. Okay, and this is a joint work with Daniel Stern, who is also talking seminar, but not about this. Okay, so this concludes my talk, my part of the talk on lambda 1. So let me talk a little bit about higher eigenvalues, and this will be the talk of the last video, the topic of the last video that I'm going to do. So for higher eigenvalues, there is something very interesting happening, that there's not necessarily smooth metric. There might not exist smooth metrics. And the first example is the second eigenvalue in the sphere. Right, so let me explain what's happening. So the one thing you can always do for higher eigenvalues, you can take one sphere here, for example, and another sphere, and you can glue them together by a tiny bridge. Right, so this should be reminiscent of the construction of the tiny handle. When I'm adding a tiny handle, only now I'm adding a tiny handle to a disconnected manifold to make it connected. Right, so what is essentially when you collapse the handle, the corresponding spectrum converges to a disjoint union of spectra of two spheres. If you think about it, the disjoint union of spectra of two spheres is just a double the spectrum of the initial sphere. Right, so what you get is that you get two zeros, right? Then 2 lambda 1 of S2, then 2 lambda 2 of S2, right, etc., etc. So everything doubles. In particular, so if this is my lambda 0, this is my lambda 1, this is my lambda 2, right? So you see that the eigenvalue is the same as before, but now area is doubled, right? So that's a construction you can always do, right? You can take two metrics, you can glue them together, and basically mush the two spectra together. Consider the union of two spectra. It turns out that for second eigenvalue of the sphere, this does give you the maximal thing. Moreover, it does the same thing happens for the third eigenvalue of the sphere. You can take three spheres, glue it together, and it works. And you can take RP2, glue sphere to it. So note you cannot glue two RP2s. If you glue two RP2s, you get different topology. But if you take RP2 and glue a sphere to it, it's still RP2. And if you arrange the ratio of those two objects in the right way, you get this value, which is actually just lambda 1 of RP2 plus lambda 1 of S2. right? So this is just, you can arrange this so that the values is just a sum of values for each component. And this turns out to be a maximal situation. All right, so looking at this, you might have natural conjecture, right? So what happened for kth eigenvalue in the sphere, k spheres glued together should be maximizer, and the same thing here, RP2 plus k minus 1 spheres is the maximizer. And recently we were able to prove this, right? So for RP2, for S2, this is true, right? So it's bounded by 8 by k. 8 by k is achieved by those glued spheres. And note that for k bigger or equals than 2, this is a strict inequality for any smooth metric, right? So there's no smooth metric which achieves the same value as this limiting construction, limiting maximizing sequence. And for RP2, we have the same kind of result, right? So RP2 plus collection of k things, k minus 1 sphere gives you what you want, right? So I will discuss the proof of these two theorems, some ideas of the proof, not the full proofs, in the fourth video, right? So now one after the next. So let me just emphasize some points from those first two introductory videos, right? So the main point in general, the one that I tried to emphasize in the first first video, is that this area represents a key interaction between spectral theory and minimal surfaces and harmonic maps in here, right? So you can use ideas from spectral theory to prove things for minimal surfaces, and you can use ideas for minimal surfaces to prove results about lambda 1. So far what I described, it was mostly in this direction, right? So we used information about minimal surfaces to prove the upper bounds for Laplacian eigenvalues. In the last video, you'll see the interaction in the opposite direction, right? Where information about Laplacian eigenvalues give you some useful information, geometric information about minimal surfaces in spheres. So one difference with maybe, if you're interested in minimal surfaces, right, you might have heard of those recent developments with like Wilmer conjecture and min-max theory, right? So I want to comment a little bit of how this interacts with that area. So the min-max theory works, min-max theory via this Almgren-Pitts theory, et cetera, via geometric measure theory. It works well for hypersurfaces, right, or codimension 1. So there are some works for codimension 2, it also can make it work, but not maybe that well as for codimension 1. So main difference here is that here we're actually talking about minimal surfaces for any codimension, right? Minimal surface in sphere of any codimension. And this is something which is very far from optimal for in this geometric measure theory context, right? So this is somehow provide a complementary picture to that, complementary set of problems to that given by classical geometric measure theory. All right, so we're talking about surfaces in any sphere, and they are mostly talking about hypersurfaces in any sphere, right? So those are very somehow orthogonal objects, as long as you're not in S3, right? In S3, it's the same. For higher spheres, those are not the same. Right, in particular, this is kind of Wilmer conjecture is one problem, which is kind of an intersection of those both areas, right? So the classical Wilmer conjecture exactly about minimal surfaces in S3. So this is resolved using these methods, but for higher dimension spheres, it's not resolved. And somehow this could give a tangible approach to that problem, right? So it's not necessarily easier maybe, but this is one way to approach it. For example, the original paper of Li Yao was exactly about Wilmer conjecture, right? So the paper where we proved the computed lambda 1 of RP2, they actually were doing something for Wilmer functional. And finally, so this is a relatively young area, right? So you see that a lot of results in recent like 5 years. And as a result, there are a lot of open questions for young graduate students and undergraduate students. Right, so let me just repeat what I'm doing for next lectures. So in the next video, I'll give some proof of this correspondence between extremal metrics, harmonic maps, and minimal surfaces, right? Something that I just skimmed over quickly So I'll give more or less detailed proof of this. And then in video 4, I'll talk about this last part with two spheres glued together. So how to approach that. So about methods. So this is a classical differential geometry here. So there'll be like some computations with like connections, maybe, et cetera, et cetera. This is very much classical algebraic geometry, classical complex algebraic geometry. All right, so I'll talk about complex structures on surfaces, and I'll talk about how to use this to construct harmonic maps with Vista correspondence. All right, thank you very much. Hopefully you will come back for video 3 and video 4.